Good day, everyone. After the wake of Renaissance period or the 16th century, the explosion of mathematical and scientific ideas across Europe was greatly evident in the 17th century, a period sometimes called as the Age of Reason. Before our Group 2, tackle more about 17th century mathematics, let us go first to our objectives for today's lesson. By the end of this lesson, you are expected to discover the 17th century inventions of machines and their effect on the theoretical mechanics and other scientific studies, determine the resolution on astronomy, identify mathematicians in this period with their more improved conceptions of mathematics, and find out the important discoveries in the field of astronomy and physics and on mathematical formulas. Now let me introduce to all of you the reporters of this group. We have first the group leader, which is yours truly, Kaakoy Alexis. I will be discussing to you the background of the 17th century and one of the mathematicians in the period. Next, we have my group members, Miss Estor Joyce, Miss Delante Laika, Miss Herolaga Angelica, Miss Bahenting Hannah, Miss Kagoyong Caroline, Mrs. Bernales Jane, Miss Ubay Marichu, Mr. Caberos Bernard, and lastly, Miss Cormanes Luisa. Each of them will discuss one of the figureheads of the 17th century. They may be mathematicians, physicists, and astronomers. After the introduction, now let us proceed to the most awaited part, the discussion. Kindly give all your attention to the discussion, everyone. Remember, the first key to learning is listening. So listen, learn, and enjoy the discussion. As you can remember, we have tackled the Old Stone Age, New Stone Age, Iron Age, and so on. Now here in 17th century, it is called as the Age of Reason because of the scientific and mathematical revolution. Also, this century is the start of mechanical age because of the invented mechanical devices. It is said they understood nature better because it was now mechanical and mechanics better because it was now mathematical. But the success of mechanical age happened later on 19th century. Based on my research, 17th century was one of the period with intense activity and innovation not just in mathematics but in different fields. The major achievements of 17th century includes scientific revolution, mechanical devices, logarithms, analytical geometry, probability, Cartesian coordinate, Pascal's triangle, and calculus. In this lesson, we will focus on these 8 figureheads of 17th century who had a very impeccable contributions in mathematics, astronomy, and physics. We have first, Jan Naper, second, Galileo Galilei, third, Johannes Kepler, fourth, René Descartes, fifth, Pierre de Fermat, sixth, Blaise Pascal, seventh, Isaac Newton, and lastly, Gottfried Leibniz. Let me introduce myself again. I am Alexis Kaakoy, the first reporter of the group, and I will be discussing to all of you Jan Naper's contribution in 17th century. First and foremost, who is Jan Naper? Jan Naper of Merkiston was born on February 1st, 1550 and died on April 4th, 1617. He was a Scottish landowner known as a mathematician, physicist, and astronomer. During 17th century, many mathematicians were aware of the issues of computations and were dedicated to relieving practitioners of the calculation burden. And that is what Naper famous for. He assisted with the issues of computations through his works. He was best known as the discoverer of logarithms. He also invented the so-called Naper's bones and made common use of the decimal point in arithmetic and mathematics. Now let us go to the first discovery of John Napier, the logarithm. John Napier published his discovery of logarithms in 1614. Mere Feci Logarithmorum Canonis Descriptio contained 57 pages of explanatory matter and 90 pages of tables of numbers related to natural logarithms. John Napier invented logarithm to speed up calculations. Logarithms vastly reduce the time required for multiplying numbers with many digits. It also paved way for scientific advances in astronomy, dynamics, and other areas of physics. In simplest definition, logarithms are just like exponents. It means that logarithms are the power to which a base must be raised to yield a given number. Expressed mathematically, x is the logarithm of n to the base b if b of x equals n, in which case one writes as x equals log of n to the base b. As you can see on the screen, we have logarithmic function. We have logarithm of x to the base a is equal to y, where if we transform it into exponential function, will result to a of y is equal to x. In our logarithmic function, variable a is the base and it is still function as base in the exponential function. The variable x in the logarithmic function will become the number yielded after raising the base. Lastly, our variable y in our logarithmic function is our logarithm, but in exponential function, it is considered as the exponent. For example, which you can see below, log of a to the base 2 is equal to 3, means 2 raised to 3 is equals to 8. So the 3 is the logarithm, and here in the exponential function, 3 is the exponent. So logarithm and exponents are the same. That's simple, right? Hope you have understood it, because now we will proceed to the two kinds of logarithms that are often used in chemistry. First, we have common or Briggian logarithm, named after the English mathematician Henry Briggs, who Napier was associated with the invention of logarithms. The power to which a base of 10 must be raised to obtain a number is called the common logarithm or log of the number. Next is natural or Naperian logarithm, named after John Napier himself. The power to which the base e, where e is equivalent to 2.718281828, must be raised to obtain a number is called the natural logarithm or ln of the number. Common logarithm is like this. Using log to the base 10, log of 100 to the base 10 is equals to 2, where it is also equivalent to 10 squared equals 100, where 10 is the base, 2 is the logarithm, the exponent or power, and 100 is the number. While natural logarithm is like this. Using natural logs carrying all numbers to 5 significant figures, ln of 30 is equals to 3.4012, where it is also equivalent to e raised to 3.4012 is equals to 30, or as I've said earlier that e is equivalent to 2.718 and so on. And since here we can see that we will use 5 significant figures, that is why e is equivalent to 2.7183, then raise it to 3.4012, and it will be equivalent to 30. So how will you get ln of 30? You just need to use your scientific calculator, press ln button, then the number 30, and lastly, the equal button. Let us proceed with the properties of common logarithm. Since I have mentioned to you that logarithm is an exponent, therefore they have the same properties. First property is multiplication property. When we are multiplying both logarithms, the operation to be used change into addition, the same as what we do in exponents. When we are dividing both logarithms, then the operation to be used change into subtraction. If dealing with exponent, you just need to transfer and put it beside the base. And if you have a negative exponent, you only need to reciprocate, and the result will always be negative. And lastly, if you are dealing with logarithm of 1 to the base x, the answer will always be 0. After the properties of common logarithm, we will continue with the properties of natural logarithm. The same as the common logarithm, but with additional properties. We have exponential and logarithmic, where e of ln x is just equivalent to x. Inverse property, ln e of x is still equivalent to x. One-to-one property of exponents, if e of x is equal to e of y, then it is the same as x equals y. Lastly, one-to-one property of logarithms, if ln x is equal to ln y, then x is equal to y. In finding logarithms, we need to use a scientific calculator. Be sure your calculator is with you, for we will try an examples now. Before we proceed, find first the logarithm or log and natural logarithm or ln buttons of your calculators. So if you are using Casio calculator, you can find the log and ln here. Have you found it? Okay, since you have found it, let us continue. So we have here the example for common logarithm. Solve for x if 6 raised to x plus 2 is equals to 21. First that you need to do is transform the equation into logarithmic equation. So it would look like this. Log of 6 raised to x plus 2 is equal to log of 21. Remember the properties of common logarithm. If we have an exponent, we transfer it beside the log, so it would look like this. X plus 2, log of 6 equals log of 21. We are looking for the value of x. In order to do that, we need to divide both sides by log of 6, so that x plus 2 will be the only left on the left side. Then it will look like this. X plus 2 equals log of 21 divided by log of 6. Now let us use our calculators. So x plus 2 will be the same first because we will be focusing more on the right side. So what is log of 21? In order to get the value of log of 21, use your calculator. Press the log button of your calculator and next is the number 21. Then lastly, press the equal button. After following my instruction, you will get an answer of 1.322219295. Then now let us find the value of log of 6 with the same process that we did with log of 21. Therefore, log of 6 is 0.77815125. Notice that the operation have changed into subtraction. It is because we are dividing both logarithms. Now let us subtract the numbers on the right side, which is equals to x plus 2 equals 0.544068044. Last thing that we need to do is transpose the 2 in order for the x to be left alone since we are solving to find the value of x. Therefore, the 2 is transposed to the right side and will become negative 2. And the final answer will be x is equals to negative 1.4559. Now let us go to our example for natural logarithm. Solve for x in e of 3x equals to 9. First that we need to do is transform the equation into natural logarithmic equation. It will look like this. Ln e of 3x equals ln of 9. Remember the properties of natural logarithm. Since we have natural logarithm e of 3x, we have to apply the inverse property. So the equation will look like this. 3x equals ln of 9. In order to find the value of x, we need to divide both sides by 3 to leave the x alone on the left side. The equation will be like this. 3x divided by 3 equals ln of 9 divided by 3. Do the calculation. 3x divided by 3 is just x. Then use your calculator to find the value of natural logarithm of 9. So first thing that you need to do is press the ln button of your calculator. Then press the number 9 and lastly the equal button of your calculator. After following my instruction, you will get an answer of 2.197224577. And since we are not dividing both logarithm, the operation stays the same and just copy the 3 and do the division. Therefore, our x is equal to 0.7324. As simple as that, class. Logarithm can also be applied to pH problem. In order to find the pH of an aqueous solution, we have the formula pH is equal to negative logarithm times hydrogen ion concentration, or in simplest form, pH is equal to negative logarithm times H+. We have an example. What is the pH of an aqueous solution when the concentration of hydrogen ion is 5 multiplied to 10 raised to negative 4 m? First that we need to do is write the formula, which is pH is equal to negative logarithm times H+. Second is we need to substitute the formula with the given data. It will now be like this. Negative logarithm open parenthesis 5 times 10 raised to negative 4 close parenthesis. Third is apply the distributive property. It will look like this. Negative log of 5 times negative log of 10 raised to negative 4. Remember the properties of logarithm. If we have a negative exponent, we need to reciprocate. Then it will be like this. Negative logarithm of 5 times negative logarithm of 1 divided by 10 raised to 4. Now we will use our scientific calculator to know the final answer. So what is negative logarithm of 5? So use your calculator and simply press the negative sign of your calculator, then the log button, the number 5, and lastly the equal button. After following all my instruction, we will get an answer of negative 0.698970004. Then now let us solve the next one. First is we divide the 1 divided by 10 raised to 4, which is equivalent to 0.0001. Then the next is press the negative sign, then the log button. Next is the number 0.0001. And lastly, the equal button. After all the instruction, we will get an answer of 4. As you can notice, the operation is changed into addition because of the multiplication property. Therefore, the pH of an aqueous solution with the given concentration of hydrogen ion is 3.3010. Now, let us proceed with the device made by John Napier. It is called the Napier's bone. So Napier published his version of Napier's bone in 1617. It is a manually operated calculating device for the calculation of products and quotients of numbers, also called rhabdology. You can see on the screen an example of Napier's bone, but this style is not the same as the original. It's another version of it. It would have been so fun multiplying and dividing if we have an actual Napier's bone. But nevertheless, this lesson will still be informative and entertaining as well. So now we have next the Napier's bone in multiplication. Our example, we will compute for 425 times 6. So first step, Napier's bones for 4, 2, and 5 are placed into the board. As you can see, we have 4 columns. The first column is for the digits 1 to 9, while the second, third, fourth columns are for the multiplicand 4, 2, and 5. In order to get the values found in each box below the multiplicand, we need to multiply the first digit multiplicand to the digits found on the first column. So for example, the multiplicand 4 is being multiplied to the first column. So for an example, we have the multiplicand 4 multiplied to the 2, which is equivalent to 8. In each box, you can see a diagonal line from the bottom left corner to the top right corner. In placing the value, if you have a single digit product just like 8, you put 8 in the bottom right triangle and you can leave the upper right triangle or put 0. Another example is the multiplicand 5 times 8, which is equals to 40. Since this is a double digit number, so the placement is like this. The first digit to the right side, which is 0, is placed at the bottom right triangle, while the second digit, which is 4, is placed in the upper right triangle. And that is how you complete the data. Next step is the sixth row is usually isolated from the rest of the board for clarity. We have separated the sixth row for our multiplier is 6. Step 3, each diagonal column is evaluated or added starting at the right side. So since we have multiplied each multiplicand to our multiplier, which is 6, then it will give us this. So each diagonal column we add it, and we should start at the right side. So we have 0 at the right side, just bring it down since it has no pair. Then the next is 2 plus 3, which is 5, and 4 plus 1 equals 5, and bring down 2 again. So therefore, the product of 425 times 6 is equivalent to 2,550. Now let us have a more complex example. So the second example is, compute for 825 times 913. Again, step 1, Napper's bones for 8, 2, and 5 are placed into the board. All the values correspond to the multiplication of each multiplicand and the first column digits are given. Next step, step 2, the ninth, first, and third rows are isolated from the rest of the board for clarity. We have separated the rows 9, 1, and 3 because it is our multiplier. Step 3, for this example, row 9, row 1, and row 3 were evaluated separately to produce the results shown below. As you can see on the evaluation of row 9, we have added a carry. It is because we can only put one digit in each box. Focus on the row 9, the 8 plus 4. It is equivalent to 12, and what you need to do is carry the first digit to the next diagonal. That explains the 4 on the next box. Step 4. Starting with the rightmost digit of the second number, the sums are placed from the rows in sequential order as seen from right to left under each other while utilizing a 0 for a placeholder. In adding all the answer, we take into account the rightmost multiplier, which is 3. And since we have it evaluated already and row 3 is equivalent to 2,475, then we do the same with the next multiplier, which is 1, with the evaluated number of 825. But then you add 0 on the right to utilize a placeholder. Therefore, it will become 8,250. Then the last multiplier, which is 9, which has the evaluated product of 7,425. And remember, you add 0 for a placeholder. And since you have already put 1 0 earlier, now we will add 2 zeros. Therefore, it will be 742,500. And last step is the rows and placeholders are summed to produce a final answer. So you add all the produced final answers. So you have 2,475 plus 8,250 plus 742,500, which is equivalent to 753,225. Therefore, the solution to multiplying 825 by 913 is 753,225. Napper's bone is not just applicable in multiplication, but also in division. So we need to find the quotient of 46,785,399 divided by 96,431. Step 1. To divide 46,785,399 by 96,431, the bars for the divisor 96,431 are placed on the board. So remember that our divisor is 96,431 while our dividend is 46,785,399. As you can see, I have already gave the evaluated product of each rows. It will help us find the quotient later on. So you have here the first row is equivalent to 96,431. The second row is 192,862 and so on. And as you can see, our dividend, which is 46,785,399, has 8-digit number. And the highest digit number found in each row is 6 only. So the final answer or the final evaluated product sa 9th row is 6-digit only. So that's the maximum digit number that we have. And our dividend is 8-digit number. So, therefore, we disregard first the two last numbers in the right side of our dividend, which is 99. Then step 2, then the greatest partial product that is less than dividend is found. In this case, 385,724. 4 is marked down as the leftmost digit of the quotient, the partial product. So the step-by-step of step 2 is like this. Remember, we have disregarded first for the meantime the last two digits from the right of our dividend. So we will focus more on 467,853. And then you need to find a product that is less than our dividend. So we have 385,724. We cannot go further than that since 482,155 is greater than the 6-digit dividend. Since the 385,724 is from the 4th row, therefore it is marked as the leftmost digit of our quotient. Then you subtract the numbers bringing down the 99. The result is 8,212,999. Step 3. The cycle is repeated until the result of subtraction is less than the divisor. The number left is the remainder. So after subtracting, we only have 8,212,999. And now, since our dividend has only 7 digits, we only disregard 1 digit, and that is the last digit, which is 9. So we will use 821,299 as our dividend. And you need to find the greatest partial product that is less than to our dividend. So we have, mas gamay sa atong dividend, we have 771,448, which is found in the 8th row. So now we have 48 as our partial quotient. Subtract the numbers, it will result to 498,519. We will not disregard any number for it is already 6-digit number. So now, find the greatest partial product that is less than to our dividend. So we have the 482,155, and that is found in the 5th row. So now we have 485 as our partial quotient. Then we subtract the numbers. It will give us 16,364. And since that is less than our divisor, which is 96,431, we cannot go further than that. Therefore, the quotient is 485 with a remainder of 16,364. The process usually stops here and the answer uses the fractional form. So therefore, our quotient in dividing 46,785,399 by 96,431 is 485 plus 16,364 over 96,431. That is all my report. I hope you have learned and enjoyed my discussion. The next reporter will be Miss Joyce Istor. Keep on listening to the other reporters class. Thank you very much.
Hello, I am Joyce, the second reporter. To continue the discussion, I'll be discussing the Galileo's Galilei inventions of machines and their effect on theoretical mechanics and other scientific studies. Galileo is the first known person who studied the skies in detail with a telescope. He made numerous significant discoveries in astronomy, including the phases of Venus and the four largest moons of Jupiter. His contributions to science include the Galilean invariance and the discovery of isochronism in pendulums. In today's language, Galileo Galilei would be called a theoretical as well as experimental physicist. First, we have the Galileo Galilei's geometric and military compass. The geometric compass was designed by Galileo Galilei in Padua in 1597 and built by Marcantonio Masolini. It is composed of two arms on which numerous lines are engraved, converging at the opening pivot, which is equipped with a hole for a plumbed line, by a quadrant marked with a variety of scales, and by a fork clamp and a slider that allows for the leg in which it is threaded to be lengthened and for the compass to be positioned vertically. This instrument of calculation allowed its users to quickly make more than 40 different types of complex geometric and arithmetic calculation and exploits the theory of proportions to solve various civil and military problems. It could be used, for instance, as a gunner's quadrant to redraw a map to scale or to calculate exchange rates. It combined two separate instruments, first for making observations by adding a quadrant to its arms, and also the calculator for solving problems in proportion, trigonometry, multiplication, and division, and for various functions such as square and cube roots. Galileo invented many mechanical devices other than the pump, such as the hydrostatic balance, but perhaps his most famous invention was the telescope. Galileo made his first telescope in 1609, modeled after telescopes produced in other parts of Europe that could magnify objects 3 times. He created a telescope later that same year that could magnify objects 20 times. With this telescope, he was able to look at the moon, discover the 4 satellites of Jupiter, verify the phases of Venus, and discover sunspots. His discoveries proved the Copernican system, which states that the Earth and other planets revolve around the Sun. Prior to the Copernican system, it was held that the universe was geocentric, meaning the Sun revolved around the Earth. In January 1610, Italian astronomer Galileo Galilei discovered 4 of Jupiter's moons, now called Io, Europa, Ganymede, and Callisto. He originally referred to the individual moons numerically as 1, 2, 3, and 4. The numerical system for naming the moons lasted for a few centuries until scientists determined that simply using numbers as a naming device would be confusing and impractical as more moons were discovered. Galileo's discovery was a pivotal point in the history of astronomy, as his observation revealed that not all celestial bodies revolve around the Earth. Until that time, Earth was thought to be the center of the universe. Its satellites, the 4 Galilean and 4 smaller moons, are closer to the planet and provide the dust that make up Jupiter's rings. The closest of the Galilean moons to Jupiter is the Io, the first moon to be discovered by Galileo. This satellite's distinctive feature is its volcanoes, make it the only celestial body in the solar system besides Earth to have volcanic activity. This moon also has sulfur dioxide snowfields, leading to its characterization as a moon of fire and ice. Io has an iron or iron sulfide core and a brown silicate outer layer, which gives its splotchy orange, yellow, black, red, and white appearance. Moving outward from Jupiter is Europa. While slightly smaller than Earth's moon, It is still one of the largest bodies in the solar system but the smallest of the Galilean satellites. Cracks and streaks crisscross the entire icy surface, which is marked with very few craters. Europa has a high degree of reflectivity, making it among the brightest moons in the solar system. At 20 to 180 million years old, the surface is fairly young. It is possible that an extensive ocean beneath the surface harbors life. Ganymede is the third Galilean moon from Jupiter and the largest of the four. This density moon is about the size of Mercury, but has about half the mass. Its outstanding characteristic is that it is the only moon to have its own magnetic field. The satellite's iron core is topped off by a thick crust that is mostly ice. 40% of the surface of Ganymede is covered by highly cratered dark regions, and the remaining 60% is covered by a light grooved terrain, which forms intricate patterns across Ganymede. And lastly, we have the Callisto, the fourth and the farthest of the Galilean moons from Jupiter. Is the most heavily cratered object in the solar system. The moon's landscape has essentially remained unchanged since its formation, which has garnered much interest among scientists. It is about the size of Mercury but very low in density. It is also experiences the less impact of Jupiter's magnetic field as its orbit is farthest from the planet and beyond Jupiter's primary radiation belt. It was Galileo's observation of Venus that proved the theory. Using his telescope, Galileo found that Venus went through phases, just like our moon, but the nature of these phases could only be explained by Venus going around the sun, not the Earth. Galileo concluded that Venus must travel around the sun, passing at times behind and beyond it, rather than revolving directly around the sun. Galileo's observation of the phases of Venus virtually proved that the Earth was not the center of the universe. It was his assertion which most endured the church leaders for the time. Galileo resumed his observation of sunspots in April 1612. In his Letters to Whistler, published in 1613, he identified sunspots correctly as marking on the suns, confirming that the sun rotated monthly as the position of the spots moved. Sunspots are dark areas of irregular shape on the surface of the sun. Their short-term and long-term cyclical nature has been established in the past century. Spots are often big enough to be seen with the naked eye, while direct observation of the sun in a clear sky is painful and dangerous. It is visible when the sun is close to the horizon or when it is covered by a thin veil of clouds or mist. And lastly, Galileo stated the basic principle of relativity. Galileo formulated the principle of relativity in order to show that one cannot determine whether the Earth revolves about the sun or the sun revolves around this Earth. Galileo's principle of relativity states it is impossible by mechanical means to say whether we are moving or staying at rest. If two trains are moving at the same speed in the same direction, then a passenger in either train will not be able to notice that either train is moving. However, if the passenger takes a fixed frame of reference, a fixed point like the Earth, he will then be able to notice the motion of either train. It also states that there is no physical way to differentiate between a body moving at a constant speed and an immobile body. And that would be all of my discussion. We will proceed to the next reporter.
Good day, everyone. I am Laika Medi Delante, and for today, I will share to you who is Johannes Kepler and his contribution. Who is Johannes Kepler? So, he was a German and was born on December 27, 1571, and was died on November 15, 1630. He was an astronomer, mathematician, astrologer, natural philosopher, and writer in music. He is a key figure in the 17th century scientific revolution, best known for his laws of planetary motion and his books Astronomia Nova, Harmonis Mundi, and Epitome Astronomiae Copernicani. These works also provided one of the foundations for Newton's theory of universal gravitation. Kepler's first major astronomical work, Mysterium Cosmographicum, or the cosmographic mystery in 1596, was the first published defense of the Copernican system. Kepler claimed to have had an epiphany on 19 July 1595 while teaching in Graz, demonstrating the periodic conjunction of Saturn and Jupiter in the zodiac. He realized that the regular polygons bound one inscribed and one circumscribed circle at definite ratios, which, he reasoned, might be the geometrical basis of the universe. After failing to find a unique arrangement of polygons that fit known astronomical observations, even with extra planets added to the system, Kepler began experimenting with three-dimensional polyhedra. He found that each of the five Platonic solids could be inscribed and circumscribed by spherical orbs. Nesting these solids, is each encased in a sphere within one another, would produce six layers corresponding to the six known planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. By ordering the solids selectively, octahedron, icosahedron, dodecahedron, tetrahedron, and cube, Kepler found that the spheres could be placed at intervals corresponding to the relative size of each planet's path, assuming the planet circled the Sun. Kepler also found a formula relating the size of each planet's orb to the length of its orbital period from inner to outer planets. The ratio of increase in orbital period is twice the difference in orb radius. However, Kepler later rejected this formula because it was not precise enough. Kepler thought the mysterium had revealed God's geometrical plan for the universe. Much of Kepler's enthusiasm for the Copernican system stemmed from his theological convictions about the connection between the physical and the spiritual. The universe itself was an image of God, with the Son corresponding to the Father, the stellar sphere to the Sun, and the intervening space between them to the Holy Spirit. His first manuscript of Mysterium contained an extensive chapter reconciling heliocentrism with biblical passages that seem to support geocentrism. The extended line of research that culminated in Astronomia Nova, or a new astronomy, including the first two laws of planetary motion, began with the analysis, under Tycho's direction, of Mars' orbit. Since completing the Astronomia Nova, Kepler had intended to compose an astronomy textbook that covered all fundamentals of heliocentric astronomy. Kepler spent the next several years working on what would become Epitome Astronomiae Copernicae, or Epitome of Copernican Astronomy. In the years following the completions of Astronomia Nova, most of Kepler's research was focused on preparations for the Rudolphine tables and a comprehensive set of ephemerides, specific prediction of planets and stars' position based on the table, though neither would be completed for many years. Kepler at last completed the Rudolphine tables in 1623, which at the same time considered as his major work. However, due to the publishing requirements of the emperor and negotiations with Tycho Brahe's heir, it would not be printed until 1627. Like Ptolemy, Kepler considered astrology as the counterpart of astronomy and as being of equal interest and value. However, in the following years, the two subjects drifted apart until astrology was no longer practiced among professional astronomers. Kepler was convinced that the geometrical things have provided the Creator with a model for decorating the whole world. In Harmonies Mundi in 1619, he attempted to explain the proportions of the natural world, particularly the astronomical and astrological
Good day, everyone. I am Angelica Hiralaga, and now I will discuss the life of the French philosopher René Descartes. And he lived 1596 until 1650. So, René Descartes was a French philosopher, mathematician, and scientist who invented analytic geometry, linking the previously separated fields of geometry and algebra. René Descartes is considered as the father of modern philosophy. He has been heralded as the first modern philosopher. Apart from other things, he wrote some of the most influential works of modern philosophy, which are still studied in university across the world. He also formulated theories, developed concepts, and made statements which became fundamental to the Western philosophy. Um, he did uh, He did groundbreaking work in physics, most prominently in the field of optics. Descartes' work on optics spanned in his entire career and represents a fascinating area of inquiry. His interest in the study of light is already on display in the intriguing study of refraction from his early notebook. So he invented the Cartesian coordinate system, developed analytic geometry, and laid the foundation of the development of calculus. So the Cartesian coordinate system is describe the position of the point in two dimensions by giving its horizontal and vertical locations, thus allowing a series of points generated by an algebraic equation to be plotted visually as a line of curve on a graph. So René Descartes provides geometric interpretations for other branches of mathematics such as linear algebra, complex analysis, differential geometry, and multivariate calculus, group theory, and more. So first is the linear algebra. So the linear algebra is a branch of mathematics that is concerned with mathematical structures closed under the operation of addition and scalar multiplication, and that includes the theory of system of linear equation, matrices, determinants, vector spaces, and linear transformations. The next is the complex analysis. So the complex analysis is the study of complex numbers together with their derivatives, manipulation, and other properties. Complex analysis is an extremely powerful tool with an unexpected large number of practical applications in the solution of physical problems. And the next is differential geometry. So the differential geometry is a mathematical discipline that studies the geometry of smooth shapes and smooth spaces, otherwise known as smooth manifolds. Using the techniques of differential calculus, integral calculus, linear algebra, and the multilinear algebra. The next is the multivariate calculus. So the multivariate calculus is the extension of calculus in one variable to the calculus with functions of several variables. The differentiation and integration of functions involving several variables other than just one. Next is the group theory. In mathematics and abstract algebra, group theory studies the algebraic structure known as groups. The concept of group is central to abstract algebra. Other well-known algebraic structures such as rings, fields, and vector spaces can all be seen as groups endowed with additional operations and assumes. In Descartes, his mathematical work laid the basis for the development of calculus. Analytical geometry of Descartes laid the foundation for the development of calculus by Isaac Newton and Gottfried Leibniz. He developed his rule of signs, a technique for determining the number of positive or negative real roots of a polynomial. He also the first to use the standard notation for the superscripts to denote powers, that is, was the first to denote the variable x squared as x to the power of 2. He independently discovered the general formula for imicable numbers. This formula is also known as Tabit-Ibn-Qurra's formula. And that's all of my discussion about the life of René Descartes and his contribution in mathematics.
Good day, everyone. I am Hannah May Bahinting. I am going to discuss the life and the contribution of Pierre de Fermat to the study of mathematics. Pierre de Fermat was born on August 17, 1601 in Beaumont-de-Lomagne, France, and died on January 12, 1665 in Castres. He was the son of a prosperous leather merchant and became a lawyer and magistrate. Pierre de Fermat was a French mathematician and lawyer. He was an early pioneer of calculus, as well as working in number theory, probability, geometry, and optics. Fermat's number theory. Fermat vainly sought to persuade Pascal to join him in the research in number theory. Fermat's number theory is inspired by an edition in 1621 of the Arithmetic of Diophantus. Diophantus is a Greek mathematician of the 3rd century AD. Fermat discovered new results in the so-called higher arithmetic, many of which concerned properties of prime number. Prime numbers is those positive integers that have no factors other than 1 and themselves. One of the most elegant of these had been the theorem that every prime of the form 4n plus 1 is uniquely expressible as the sum of two squares. A more important result, now known as Fermat's little theorem, asserts that if p is a prime number and if a is any positive integer, then a raised to p minus a is divisible by p. Fermat seldom gave demonstrations of his results, and in this case, proofs were provided by Gottfried Leibniz, the 17th century German mathematician and a philosopher, and Leonhard Euler, the 18th century Swiss mathematician. For example, if a is equals to 2 and p is equals to 7, then 27 is equals to 128, and 128 minus 2 is equals to 126. So 7 times 18 is equals to 126. So 7 times 18 equals 126 is an integer multiple of 7. If a is not divisible by p, Fermat's little theorem is equivalent to the statement that a raised to p minus 1 equals 1 is an integer multiple of p, or in symbols, a raised to p minus 1 is equals to 1. These numbers are called Fermat's numbers, and when a Fermat number is prime, it is called Fermat prime. The only known and proven Fermat primes are for the cases when n is equals to 0, 1, 2, 3, and 4. These numbers are extremely important to the study of prime numbers and Mersenne numbers, both of which is strongly studied in number theory. For occasional demonstrations of his theorems, Fermat used a device that he called his method of infinite descent. It is an inverted form of reasoning by recurrence or mathematical induction. Fermat was the most productive mathematician of his day. He is known for his great or last theorem. This appeared in the margin of his copy of Diophantus Arithmetica and states that the equation x raised to n plus y raised to n is equals to z raised to n, where x, y, z, and n are positive integers, has no solution if n is greater than 2. This theorem remained unsolved until the late 20th century. In the middle 1630s, Pierre de Fermat studied the study of curves and equations. He generalized the equation for the ordinary parabola ay is equals to x squared to a negative 1y is equals to x raised to n. The curves determined by this are known as the parabolas or hyperbolas of Fermat. During the same years, he found formulas for areas bounded by these curves through a summation process that is equivalent to the formula now used for the same purpose in the integral calculus. Mathematician Isaac Basel Fermat was a French mathematician who wrote in the years 1657 to 59. He showed that certain algebraic curves were strictly rectifiable. Fermat also solved the related problem of finding the surface area of a segment of parabola of revolution. Fermat's principle in optics. Pierre de Fermat, a French mathematician's principles in optics is useful in the study of optical devices because it states that light traveling between 2 points seeks a path such that the number of waves, the optical length, is equal to that in neighboring paths. Another way of stating this principle is that the path taken by a ray of light requires either a minimum of a maximum time. Thus, two beams of light diverging from a distant object point and converge by a lens to an image point will have identical optical path lengths.
Good day, I am Caroline Caguyong and I'm going to discuss who was Blaise Pascal. Blaise Pascal was a 17th century mathematician and philosopher who made great contribution to both fields. He was born on June 19, 1623. His mother died when he was about 3 years old, so his father moved Blaise and his two sisters and took charge of educating them. His dad worried that Blaise would reject the classics, so he banned math in their studies. Blaise took studying geometry behind his dad's back and made up a lot of his own geometry terms. As a teenager, he started working on calculating known as Pascal calculator of in 30 years. He built 20 machines and 50 prototypes, including one of the first mechanical calculators, but it wasn't a huge commercial success. It was cumbersome and it was really expensive. It became more of the status symbol for the rich than actual machine. You might heard of Pascal triangle. Pascal is also credited with coming up with Pascal's triangle. It is a triangle of numbers where each number in the two numbers directly above it added together, except for the ages, which are all 1. These create patterns along diagonals in the rows and can be used to solve things like probability, combinations, and exponent. Pascal may have been a man of science, but his most famous work was entirely unscientific. He had one of the most unique perspectives on religion and faith, particularly the belief in God. Pascal was by no means the first scientist to question or attempt to prove or disprove the existence of God, but his take was unique in its pragmatism. The way he saw it like a mathematician, the odds of success were what mattered. If you do believe in God and He exists, you win. If He doesn't, well, nothing lost, nothing gained. So Pascal argued, bet on God, you have nothing to lose. So let's proceed to the 10 interesting facts about Blaise Pascal. So the first one is Blaise Pascal was a child prodigy. Pascal showed a really impressive propensity for math and science in particular. When he was 16 years old, he wrote a treatise on something called the mystic hexagram. This treatise is still known today as Pascal's theorem. Next, Blaise Pascal almost died as a child. When Pascal was only 1 year old, he suddenly became very ill with an unknown disease. His stomach swelled up and he became prone to violent fits in which he would thrash around in his bed. At the time, friends and family assumed it was due to witchcraft. Welcome to the 17th century. Ladies and gentlemen, we all know diseases were chalked up to witches and sorcerers. Neighbors blamed an elderly woman that had been caring for Pascal. At first, His father pushed aside the rumors, but when Pascal showed no signs of recovery, he also began to blame the old woman. Under pressure, she admitted to casting a spell on poor little Pascal. According to the woman, the only way to cure Pascal was to transfer the spell onto something else. They applied special herbs to Pascal's stomach and brought in a two stray cats. Mysteriously, Pascal began to feel better within a week. Those poor cats. Next, Pascal's theorem is named after Blaise Pascal. Pascal's theorem is a theorem in projective geometry. If you're not a geometric aficionado, it's a little bit complicated to explain. But if you're interested, it states that if a hexagon is inscribed in a conic, then the 3 points at which the pair of opposite sides meet lie on the straight line. Are you confused? Me too. But this was groundbreaking stuff when Pascal came up with it. Plus, he was just 16 years old when he came to his conclusions. This was so shocking that when Pascal sent his theorem to the famous French mathematicians, Descartes, he thought that his father had written it. Pascal was clearly a precocious and intelligent young person. This was just the beginning of his impressive career. Next, Blaise Pascal is one of the inventors of the original mechanical calculator. I think that today we take calculators for granted. Whenever we need help with math, we can easily pull out our smartphones and plug in a few numbers, easy peasy. That wasn't the case in the 17th century, until Pascal came along. When Pascal's father was working as a tax supervisor in Rouen, the young mathematician saw a need for a machine that would help with all of the tiresome calculations. There had to be an easier way. And so started Pascal's 3 year project to create a mechanical calculator. Pascal designed the original machine in 1642 when he was 19 years old. He went on to create 50 prototypes before he presented his findings in 1645. He then went and produced 20 more models over the next 10 years, when finally he was granted a royal privilege by King Louis XIV. A royal privilege is similar to a patent, and calculators will call Pascal's calculator from there on out. Next, Blaise Pascal contributed much to the study of geometry. Over his lifetime, he contributed much to the philosophy of mathematics, which is a branch of philosophy that studies, you guess it, the principles of math. His major contribution was a work of writing called De L'Esprit Geométrique, or of the geometrical spirit in English. Inside, Pascal discussing the questions of discovering truths in geometry. He also developed a theory of definition in of the geometrical spirit. Pascal discerned the difference between definitions that are used and defined by writers and definitions that occur within languages as a whole and which are innately understood by native speakers. Next, Blaise Pascal invented the syringe. In addition to his contribution to the field of mathematics, Pascal also contributed much to the field of hydrodynamics and hydrostatics, which were based on his findings on the principle of hydraulic fluids. One important invention that came out of his work was hydraulic fluids in the syringe. He was able to create this valuable innovation thanks to what is known today as Pascal's law. Pascal's law states that a pressure change at any point in a confined incompressible fluid is transmitted throughout the fluid so that the same change occurs everywhere. This idea makes a syringe possible. Next, Blaise Pascal was very religious. In 1646, Pascal slept and fell, breaking his hip. This near-death experience profoundly changed the mathematician, and he subsequently became very religious. Pascal was a follower of Jansenism, a branch of Catholicism. Jansenists believed that salvation could only be achieved by the grace of God, not through moral acts. Scholars usually refer to this as Pascal's first conversion. He began to write theological texts soon after. His second conversion occurred in 1654. According to Pascal, he had a religious vision. He wrote down that he experienced, describing it as such, fire, God of Abraham, God of Isaac, God of Jacob, not of the philosopher and the scholars. Next, Blaise Pascal wrote many important theological works. The most important theological texts that Pascal wrote are letters provincials, thoughts, spoke on and defended the Christian faith, and is considered to be Pascal's most influential theological work. It was incomplete at the time of his death. It was published posthumously. It is also considered to be a landmark in the world of French prose. Next, Blaise Pascal invented the first form of modern public transportation in Paris. One of Pascal's last major accomplishments was the first form of public transportation in Paris. It was called the Carrousel à quai seuls and can be compared to a modern bus system. In the late 17th century, Paris boasted 500,000 residents, 500 major roads, and 9 bridges. With all of those residents and streets, a form of shared public transportation became necessary. That's where Pascal came in. He created a system of large horse-drawn carriages. These involve a large carriage pulled by 4 horses, a valet, and a driver. The carriages were able to house 8 passengers and followed specific routes. The carriages stopped when the passengers requested, or when there were passengers waiting at distinct stops. Sounds just like a bus, right? Last, Blaise Pascal died at the young age of 39. Pascal suffered from fair health his entire life. He often had headaches and stomach aches. After the death of one of his sisters, his health began to severely decline, rendering him bedridden. Pascal knew that he was dying, so he requested to be moved to a hospital to live out his final days. But he was so sick that he couldn't be moved. He died in 1662. After his death, an autopsy was performed on his body which showed signs of tuberculosis, stomach cancer, and many other maladies. His body has since been moved inside the church along with French playwright Jean Racine. So, even if you aren't an expert mathematician or theologist, Blaise Pascal is definitely worth learning about. He contributed so many important innovations to his fields, and the world wouldn't be the same without his inventions. I hope you enjoy learning more about Mr. Pascal. Thank you and God bless.
Good day everyone, my name is Jane Bernales and I'm the 7th reporter of the group. And I will continue the report of Ms. Caroline Cagoyong about Blaise Pascal's inventions and discoveries. The first is the Pascal theorem. In projective geometry, Pascal theorem states that if 6 arbitrary points are chosen on a conic and joined by line segments in any order to form a hexagon, then the 3 pairs of opposite sides of the hexagons meet at 3 points which lie on a straight line called the Pascal line of the hexagon.
Next, the Pascal triangle. Pascal triangle is a kind of number pattern. Pascal's triangle is the triangular arrangement of numbers that gives the coefficients in the expansion of any binomial expression. The numbers are so arranged that they reflect as a triangle. Firstly, 1 is placed at the top, and then we start putting the numbers in a triangular pattern. The numbers which we get in each step are the addition of the above 2 numbers. It is similar to the concept of triangular numbers. Pascal triangle definition. Most people are introduced to Pascal triangle through an arbitrary seeming set of rules. Begin with 1 on the top and with 1 running down, the 2 sides of a triangle. Each new number lies between 2 numbers and below them, and its value is the sum of the 2 numbers above it. The theoretical triangle is infinite and continues downward forever, but only the first 6 lines appear in a figure 1. A different way to describe the triangle is to view the first line as an infinite sequence of zeros, except for a single one. To obtain successive lines, add every adjacent pair of numbers and write the sum between and below them. The non-zero part is Pascal's triangle. Properties of Pascal triangle. Each number is the sum of the 2 numbers above it. The outside numbers are all 1. The triangle is symmetric. The first diagonal shows the counting numbers. The sums of the rows give the powers of 2. Each row gives the digits of the power of 11. Each entry is an appropriate choose number, and those are the binomial coefficients. The Fibonacci numbers order along the diagonals. Next is the Pascal line. Pascal calculator also known as the arithmetic machine or Pascal line, is a mechanical calculator invented by Blaise Pascal in the mid-17th century. Pascal designed the machine in 1642. Pascal was led to develop a calculator by the laborious arithmetical calculations required by his father work as the supervisor of taxes. He designed the machine to add and subtract two numbers directly and to perform multiplication and division through repeated addition or subtraction. Pascal calculator was especially successful in the design of its carrying mechanism, which adds 1 to 9 on one dial and carries 1 to the next dial. When the first dial changes from 9 to 0, his innovation made each digit independent of the state of the others, enabling multiple carries to rapidly cascade from one digit to another, regardless of the machine's capacity. Pascal was also the first to shrink and adapt for his purpose a lantern gear used in turret clocks and water wheels. These innovations allowed the device to resist the strength of any operator input with very little added friction. The Pascal line is a direct adding machine. It has no crank, so the value of a number is added to the accumulator as it is being dialed in. By moving a display bar, the operator can see either the number stored in the calculator or the complement of its value. Subtractions are performed like additions using some properties of nines complement arithmetic. The nines complement of any one-digit decimal number d is 9. So the nines complement of 4 is 5, and the nines complement of 9 is 0. Similarly, the 11's complement of 3 is 8, and a decimal machine with n dials the nines complement of a number. Are there steps in resetting the machine? The machine has to be rezeroed before its new operation. The method of rezeroing the Pascal chose, which propagates a carry right through the machine, is the most demanding task for a mechanical calculator and proves before each operation that the machine is fully functional. This is a testament to the quality of the Pascal line because none of the 18th century criticisms of the machine mention a problem with the carry mechanism. Raise zero. Set all the wheels to their maximum using the marks onto adjacent spokes. Every single wheel is ready for a carry transfer. Add one to the rightmost wheel. Each wheel sends to its suitor to the next one. The zeros appear one after another like in a domino effect from right to left. The second table is for addition. Additions are performed with the display bar moved, close set to the edge of the machine showing the direct value of the accumulator. After zeroing the machine, numbers are dialed in one after the other. Addition. The machine is at 0. The operator enters 12,345. The operator enters the second operand 56,789. If he starts with the rightmost number, the second wheel will go from 4 to 5 during the inscriptions of the 9 because of a carry transmission. The third table is for subtraction. Subtractions are performed with the display bar move close sets to the center of the machine, showing the complement value of the accumulator. Change display space. Move the display bar down to uncover the complement part of each result cylinder. From this point on, every number dialed into the machine adds its value to the accumulator and therefore decreases the total displayed in the complement window. Enter the nines complement of the minuend. The operator can either use the inner wheels of complements or dial the nines complement of 54,321 or 45,678 directly. Dial the subtrahend 12,345 on the spoke metal wheels. This is an addition. The result is 41,976 in the nines complement window. The next is the theory of probability. Pascal was the first to quantify the quality of probability in an honest die roll. Pascal devised his theory of probability through correspondence. It was based on a classical problem in probability theory called the division of the stakes, which mathematicians have been discussing for around 200 years. It was one of the famous problems that motivated the beginnings of modern probability theory, in the 17th century, and it led Blaise Pascal to the first theories about what today is known as unexpected value. The problem concerns a game of chance with two players who have equal chances of winning each round. The players contribute equally to a prize pot and agree in advance that the first player to have won a certain number of rounds will collect the entire prize. Now, surprised that the game is interrupted by external circumstances before either player has achieved victory. How does one divide the pot fairly? It is tacitly understood that the division should depend somehow on the number of rounds won by each player, such that a player who is close to the winning will get a larger part of the pot. But the problem is not merely one of calculation. It is also involves deciding what a fair division actually is. The next is the atmospheric pressure. The substance of the atmosphere has been one of the oldest subjects of scrutiny by natural scientists and philosophers the world over. The Greeks identified air as one of their 5 fundamental elements of matter, but it wouldn't be until the 17th century that the emergence of modern scientific techniques that the air around us would begin to be scientifically described. Pascal studied the works of Galileo and the Italian physicist Evangelista Torricelli and began conducting his own experiment to measure the atmosphere. His experiments measured the atmospheric pressure and paved the way for further studies in hydrodynamics and hydrostatics. A unit of atmospheric pressure is called a Pascal in honor of this contribution. One set measured mercury levels at the base and top of a tower in Paris, and one set measured mercury levels at various points along a mountain. In both cases, Pascal observed that the level of mercury in the tube changed in response to its height. These experiments proved that the atmospheric pressure varies depending on altitude, and this relationship can be measured using a barometer. The last is the Pascal's law. Pascal's law is a principle in fluid mechanics given by Blaise Pascal that states that a pressure change at any point in a confined incompressible fluid is transmitted throughout the fluid such that the same change occur everywhere. In his experiments on atmospheric pressure, Pascal developed several major innovations as a way to study and measure the atmosphere. One of the most widely used is the hydraulic press, which distributes force through a liquid from one place to another. This system is essential to industrial processes and machinery today and relies on what's become known as Pascal's law. Pascal's law states that when there is an increase in pressure at any point in a confined fluid, there is an equal increase at every other point in the container. This law and the experiments that Pascal developed to identify it were essential for the development of the modern field of hydrodynamics. Pascal's principle is defined as a change in pressure at any point is an enclosed fluid at rest is transmitted and diminished to all points in the fluid. Pressure exerted on a fluid is an enclosed container is transmitted equally and undiminished to all parts of the container and acts at right angle to the enclosing walls. Alternate definition, the pressure applied to any part of the enclosed liquid will be transmitted equally in all directions through the liquid. A typical application of Pascal's principle for gases and liquid is the automotive lift seen in many service stations. Increased air pressure produced by an air compressor is transmitted through the air to the surface of oil in an underground reservoir. The oil in turn transmits the pressure to a piston which lifts the automobile. The relatively low pressure that exerts the lifting force against the piston is about the same as the air pressure in automotive tires. Hydraulics is employed by modern devices ranging from the small to enormous. Pascal's barrel. Pascal's barrel is the name of a hydrostatics experiment allegedly performed by Blaise Pascal in 1646. In the experiment, Pascal supposedly inserted a long vertical tube into a barrel filled with water. When water was poured in the vertical tube, the increase in hydrostatic pressure caused the barrel to burst. an illustration of Pascal Babel experiment from the pursuits of nature. The experiment is mentioned nowhere in Pascal's preserved works, and it may be apocryphal attributed to him by 19th century. The legacy of Blaise Pascal. At once a physicist, a mathematician, an eloquent publicist in the Provinciales, and an inspired artist in the Apology and his private notes, Pascal was embarrassed by the bare abundance of his talents. It has been suggested that it was his too concrete turn of mind that prevented his discovering the infinitesimal calculus, and in some of the Provinciales, the mysterious relations of human beings with God are treated as if they were a geometrical problem. But these considerations are far outweighed by the profit that he drew from the multiplicity of his gifts. His religious writings are rigorous because of his scientific training, and his love of the concrete emerged no less from the stream of quotations in the Provinciales than from his determination to reject the rigorous method of attack that he has used so effectively in his apology.
And I will end my topic in a Blaise Pascal quote, which is, "If I believe in God and life after death and you do not, and if there is no God, we both lose when we die. However, if there is God, you still lose and I gain everything." That's all. Thank you.
Good day, everyone. I am Mari Chubay, the eighth reporter of the group, and I'm going to discuss Isaac Newton's discoveries and inventions. So, who is Isaac Newton? Isaac Newton's full name is Sir Isaac Newton, PRS, who was born January 4, 1643 and died March 31, 1727. He was the son of a farmer who died 3 months before he was born. Newton spent most of his early years with his maternal grandmother after his mother remarried. His education was interrupted by a failed attempt to turn him into a farmer, and he attended the King's School in Grantham before enrolling at the University of Cambridge Trinity College in 1661. He was an English physicist and mathematician who was the culminating figure of the scientific revolution of the 17th century. He was a key figure in the philosophical revolution known as the Enlightenment. Isaac Newton, known as the man who discovered gravity, motion, and invented calculus. Isaac is widely known for his published work Philosophiae Naturalis Principia Mathematica in the year 1687, commonly known as the Principia. Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy, which established the three laws of motion and the law of universal gravity. Newton's three laws of motion state that every object in a state of uniform motion will remain in that state of motion unless an external force acts on it. Second, force equals mass times acceleration. And the third, for every action there is an equal and opposite reaction. Principia propelled Newton to stardom in intellectual circles, eventually earning universal acclaim as one of the most important works of modern science. So Newton's works and discoveries in mathematics are: he was the original discoverer of the infinitesimal calculus. His theory of calculus built on earlier work by his fellow Englishmen John Wallis and Isaac Barrow, as well as on work of such continental mathematicians as René Descartes, Pierre de Fermat, Bonaventura Cavalieri, Johann van Waveren and Gilles Personne de Roberval. Calculus, known in its early history as infinitesimal calculus, is a mathematical discipline focused on limits, continuity, derivatives, integral, and infinite series. Isaac Newton and Gottfried Wilhelm Leibniz independently developed the theory of infinitesimal calculus in the late 17th century. By the end of the 17th century, both Leibniz and Newton claimed that the other had stolen his work, and the Leibniz-Newton calculus controversy continued until the death of Leibniz in 1716. Do you know that before Newton and Leibniz, the word calculus referred to any body of mathematics, but in the following years, calculus became popular term for a field of mathematics based upon their insights. Newton came to calculus as part of his investigation in physics and geometry. He viewed calculus as the scientific description of the generation of motion and magnitudes. So there are discoveries of Newton in mathematics that is part of calculus. First, the average slope of a curve. Differentiation or derivative approximates the slope of a curve as the interval approaches zero. The integral of a curve can be thought as the formula for calculating the area bounded by the curve and the x-axis between two defined boundaries. So for example, on a graph of velocity against time, the area under the curve would represent the distance traveled. Essentially, integration is based on a limiting procedure which approximates the area of a curvilinear region by breaking it into infinitesimally thin vertical slabs or columns. In the same way as for differentiation, an integral function can be stated in general terms, the integral of any power, and there are other integral functions for exponential and logarithmic functions, trigonometric functions, etc., so that the area under any continuous curve can be obtained between any two limits. A second line is a straight line joining 2 points on a function. It is also equivalent to the average rate of change or simply the slope between 2 points. The average rate of change of a function between 2 points and the slope between 2 points are the same thing. A tangent line or the blue line is a straight line that touches a function at only one point. The tangent line represents the instantaneous rate of change of the function at that one point. The slope of the tangent line at a point on the function is equal to the derivative of the function at the same point. Next is methods of fluence. The area under a curve can be approximated by summing the area of a number of rectangles or slabs drawn within it. The greater the number of the rectangles used, the thinner the slabs. The more accurate the approximation, so the green area below is a better approximation than the yellow. Integration gives an area based on an infinite number or of slabs and so approaches the exact area. The opposite of differentiation is integration or integral calculus, or in Newton's terminology, the method of fluence. And together, differentiation and integration are the two main operations of calculus. Newton's fundamental theorem of calculus states that differentiation and integration are inverse operation. So methods of fluence are the opposite of the average slope of a curve. So that if a function is first integrated and then differentiated or vice versa, the original function is retrieved. And lastly, the generalized binomial theorem. Newton's method for approximating the roots of a curve by successive iterations after an initial guess. Generalized binomial theorem describes the algebraic expansion of powers of a binomial. an algebraic expression with two terms such as a squared minus b squared. He made substantial contributions to the theory of finite differences, mathematical expressions of the form f of x plus b minus f of x plus a. He was one of the first to use fractional exponents and coordinate geometry to derive solutions to Diophantine equations or the algebraic equations with integer-only variables. He developed the so-called Newton's method for finding successively better approximations to the zeros or roots of a function. He was the first to use infinite power series with any confidence. And for the other discoveries and inventions of Isaac Newton, Mr. Cabarrus will discuss further.
I'm Bernard Cabarras, and I'm here to tackle about Isaac Newton books and invention. So first is optics. Optics is Newton's discovery of the composition of white light, integrated the phenomena of colors into the science of light, and laid the foundation for modern physical optics. It is a book about a theory of the reflection, refraction, inflection, and the colors of light. So next is mechanics. Mechanics is three laws of motion. The basic principle of modern physics resulted in the formulation of the law of universal gravitation. So the three laws are law of inertia, law of mass, and acceleration, and the third law of motion. According to the first law, unless a force acts on an object, it will not modify its motion. The second law, the force of an object is equal to its mass times its acceleration. The third law states that they applied forces of equal magnitude and opposing direction to each other. And that's the three law of motion. Next is Newtonian telescope. It was invented in 1642 to 1727. English physicist Sir Isaac Newton invented a reflecting telescope called Newtonian telescope, also known as Newtonian reflector, or just Newtonian, by using a concave mirror, primary mirror, and a flat diagonal secondary mirror. And here is a picture of Newtonian telescope. And that's all. Thank you.
Who is Gottfried Wilhelm Leibniz? Gottfried Wilhelm Leibniz, also known as von Leibniz, born in Leipzig, Saxony on July 1, 1646 and died on November 14, 1716. His father is Friedrich Leibniz, a professor of moral philosophy at the city's university, died when Leibniz was only 6. And his mother is Katharina Smock, who was the daughter of a rich local lawyer. Gottfried Wilhelm Leibniz was a philosopher and mathematician, known for a number of important contributions to mathematics and philosophy. Gottfried Leibniz's major contribution to mathematics was his discovery of the binary numeral system, or the base 2 system, which we find today in computers and related devices. Binary code is the language of computers and electronic devices. Leibniz's binary system was more of a way to combine his philosophy and religious beliefs with math, and didn't have much purpose. That changed when the first computers were developed in the early 20th century around the time of World War II. These early computers needed a limited language to control its functions, so early computer scientists used binary to represent on and off, or ones and zeros. As computers became more sophisticated, binary code became the most used language. Leibniz's development of the code set the foundation to bring forth the digital age almost 300 years before. With modern computers continuing to improve, researchers strive to go beyond computers knowing only binary code. He is also noted for his independent invention of the differential and integral calculus. Leibniz, alongside Newton, was at the forefront of the development of calculus. Leibniz also introduced several important notations that are still used to this day. For example, the integral sign, the question mark. The rule of differential calculus is still called Leibniz law, and the theorem that tells how and when to differentiate under the integral sign is known as the Leibniz integral rule. In 1671, Leibniz began work on an invention that would be able to do all four math operations, such as the addition, subtraction, multiplication, and addition. His invention was called the step reckoner, so he continued to work on it and improve it over a number of years. Gottfried Wilhelm Leibniz (1646 to 1716) was one of the great thinkers of the 17th and 18th century and is known as the last universal genius.
Thank you very much for that very profound and understandable report, reporters. As a group, we hope that you have understand and learned a lot and especially had fun throughout the discussion. If you ever want to know more, understand more, or dig deeper to our topic 17th century mathematics, you can go through this link. It will directly direct you to a lot of information that you want to know more. Thank you very much, everyone. God bless us all and advance Merry Christmas!